Hi, this is OrgoChemSimplified, and today we're doing a mechanism problem with epoxides. And so what we see here is we have an epoxide and an alkene. We're reacting that with an acidic compound HCl, which is essentially just H+. And what we get is this cyclohexane with a double bond and an alcohol. So clearly we've gone from an epoxide to an alcohol. What that means is this ring was open. And how is it open? Well, we have an acid, so that it's an acid catalyzed ring opener, right? So we start with an acid. So how do acids react with compounds? Well, they protonate compounds. And what gets protonated? Well, the most basic atom gets protonated. So what's the most basic atom in this molecule? The most basic atom in this molecule is this oxygen on the epoxide. So what happens is, we have this oxygen on the epoxide, and it grabs the H+ from HCl. And what we get is just a protonated compound. Here. Now this three-membered ring is very unstable, so it's going to want to open. It can do that either by grabbing this bond right here or this bond right here. Well, let's think about what happens. If we grab this bond right here, we're taking away the electrons from this tertiary carbon. We're grabbing the electrons from the secondary carbon, right? So the carbocation would be on the secondary carbon. Whereas this one, if we took those electrons, if we took that bond away, we'd be taking an electron from the tertiary carbon, so the carbocation would be on the tertiary carbon. Which one is more stable? The tertiary carbocation is going to be more stable than the secondary carbocation. So what happens is, because the tertiary carbocation is more stable, this is the bond that's going to break, and what we get is that tertiary carbocation. So let's draw it. You have a positive charge right here, an OH group, and a double bond. Okay, so now we have a positive charge and we want to get rid of it, right? Well, how do you get rid of a positive charge? You need a nucleophile, right? So what nucleophiles do we have? Well, the only nucleophile that we have in this structure, besides the one that's next to it, right? If we use this OH group as a nucleophile, we're just going backwards. So we need another source of electrons, and the other source of electrons is this double bond right here. So what actually is going to happen is this double bond will come down and actually attack that carbon and form another carbocation. So what we get is a 1, 2, 3, 4, 5, 6-membered ring. And we had 2 carbons attached here. And this carbon is attached to this isopropyl group, right? And wherever the positive charge is wherever that electron is taken from. So this carbon's still part of the ring, so it still has an electron here, but this electron was taken away and given to that carbon, right? So the positive charge is actually on this tertiary carbon right here. And so what's the difference between this compound and the compound that is supposed to be a product? Well, the only difference is this is now a double bond, right? So you need a source of electrons to quench that positive charge, and the only place you would get that source of electrons is from a CH bond, right? So a CH bond is going to have to contribute to that positive charge to form the double bond. Well, that's practically deprotonation. So what do we need to do? We just take the most basic atom. The most basic species we have in solution is just a Cl-. And that forms us our product. That should agree with this molecule right here, which I believe it does. So even though this mechanism is sort of complicated, you're able to break it down using your basic principles, right? You know generally how each species reacts and what needs to happen, so you can walk through the mechanism and actually get to the answer. So let's see what we did here. We had an epoxide. We knew it was very unstable and we needed to open it. How do we do that? We use a acid catalyst. So we protonated that epoxide. The epoxide had to open. Now we had a choice. Which of these two carbons is going to give up its bond? Well, it's going to be the one that produces the most stable carbocation. And so that's the tertiary carbon. And then we knew we needed to form the six-membered ring and quench that positive charge. So we had to use our source of electrons, which was our alkene double bond. And now we needed to form another double bond to get the product. So we needed a source of electrons. The only source of electrons was that CH bond. So you had to deprotonate that proton and form the double bond. So you don't need to memorize how to do a certain mechanism if you know the general reactivity. And hopefully that provided you with some insight into solving mechanism problems. If you liked the video, please share it with your friends. I want to help as many people as possible. And thanks for watching.